I think we are about to start. So
Yeah.
Yanni is the host of today's meeting. So I'll just let Yanni get started.
Sure. Thank you.
Your call. Whenever you want to start, we can.
Yeah. So welcome everyone to the second talk of the one-word signal processing seminars. And today we have Professor Waheed Bajwa from Rutgers University. So let me first start with the procedure of today's seminar. So today's seminar will be, first of all, today's seminar will be recorded and will also be streaming on YouTube, and later will be uploaded on YouTube and Bilibili, so you can access the videos afterwards. And all the audience, please either hold your questions until after the talk, or you can also type in your questions in the chat box. So let's just try not to interrupt during the talk, and we will try to relay the questions after the talk, or you can ask afterwards. So now let me first introduce today's speaker, Professor Waheed Bajwa. His research interests include statistical signal processing, high-dimensional statistics, machine learning, inverse problems, and networked systems. He is currently an associate professor in the Department of ECE and an associate member of the graduate faculty of the Department of Statistics at Rutgers University. He has received a number of awards in his career, including the U.S. Army Research Office Young Investigator Award, the U.S. National Science Foundation Career Award. He has also been involved in a number of professional activities, including serving as the lead guest editor for a special issue of IEEE Signal Processing magazine on distributed streaming machine learning, a technical co-chair of IEEE Spock workshop and Asiloma conference, as well as an associate editor of IEEE Signal Processing letters. He is currently serving as a senior area editor for IEEE Signal Processing letters, an associate editor for IEEE transactions on signal and information processing over networks, and an elected member of the Sensor Array and Multi-Channel and Signal Processing for Communications and Networking Technical Committees of IEEE Signal Processing Society. I was very lucky to have the opportunity to listen to Professor Bajwa's talks in various conferences ever since I was a graduate student, and I really liked his talks. So now let's welcome Waheed to give his talk on high-dimensional regression and dictionary learning, some recent advances for tensor data. So Waheed, please get started.
Thank you, Yanning, for the very kind introduction. I'd like to begin by thanking all the organizers of this seminar series. I think it's a perfect thing to have in a pandemic and also after the pandemic is over. So special thanks to all the organizers. So also welcome to everyone who is listening from across the world. Hopefully the time is not too inconvenient for anyone. I'm going to talk about high-dimensional regression and dictionary learning, and I'll explain that a little bit, what I mean by that, and also discuss it in the context of tensor data. I want to begin by thanking, first of all, the sponsors who have funded the research, the National Science Foundation of the United States and the Army Research Office. And I especially want to acknowledge that this research wouldn't have been possible without my wonderful colleagues and collaborators and students. The students of mine who worked on this, Talal Ahmed, Zahra Shakiri, Harun Raja. Unfortunately for me, fortunately for them, they all graduated last year. So they are all now gainfully employed. This work also involves work with my collaborator, Anand Sarwate, and his student, Mohsen Ghassemi. Okay, so just to give you a sense of what the talk is going to be about, I have divided it into three pieces. The first piece is basically motivating why we are doing what we are doing. in particular, clarifying the meaning of high dimensional data, which is more well known in the statistics community than in the signal processing communities. Then talk about high dimensional tensor regression, and depending upon how much time I'm left with, I'll talk about dictionary learning for tensor data, and then I'll summarize. Yanning already mentioned that if you have questions, please type them in the chat box. I left it to the organizers that if there are any questions that perhaps will be detrimental to your understanding, then perhaps they can actually interrupt me during the talk, and we can have an interactive conversation, because the idea is at the end of the day that you leave this talk with having learned something. And if we can accomplish that goal, I think it will be I would consider it a successful talk. Okay, so let's talk about high dimensional data and its implications. So we are all students of signal processing statistics, and we have been doing, for example, inference problems for decades. Now, what happened if you, for example, pick up classical texts like this Stephen Kay's book or other statistics texts? It used to be that data in classical signal processing, machine learning, and statistics problems, it used to be extrinsically low dimensional. Now, what do I mean by low dimensional? It's all a relative term. So by low dimensional, we meant that the number of data samples exceeds the number of features or the number of unknowns in each sample. So the examples exist in social sciences, medical sciences, paleontology, communications, array processing, all those things. And just pick the example of classical linear regression. So here are some notation I'm going to set that will be used later. So let's say you were doing linear regression, which is you have some response variable y. For example, this could be observations from a radar or an array sensor array. And you have p predictors or covariates, and you have n greater than or equal to p observations. So classically, what you do is you build this linear system of equations, y equal to x beta. Beta is unknown. You might have seen it as y equal to h theta, doesn't matter what you call it. So we have x and y is known, beta is unknown. Beta has p parameters, and we have n observations. And if n is greater than or equal to p, so the number of observations exceeds the number of features that you have, this is low dimensional setting. P can be as large as you want, as long as the number of samples exceeds it, we are in a low dimensional setting. What's the advantages of low dimensional setting? It is that the advantage is that there is less fear of overfitting, the memory requirements can be low, and the computations can be easier. Well, this is all good, but now we are living in a world where we have cheap sensors, abundant storage, and digitization of the world that has led to a shift to high dimensional inference problems. So what do we mean by high dimensional? It's again relative. The idea is that the dimension of the data, the things you are trying to learn about, the number of features, independent variables, predictors, that far exceeds the number of samples. So that is what is called high dimensional data. It's a relative term. It really depends upon how many observations you have. And the examples today are, so again, the same problems, but now we are collecting way more data. For example, medical sciences, you are now able to collect fMRI data, MRI data, EEG data, ECG data. But if you study many medical problems, the number of subjects, which are the number of observations, the number of patients you have, it's maybe 1,000, 2,000, 3,000, and the dimensionality of data can be in tens of thousands. So we are in a very high dimensional regime. So what's the challenge with high dimensional data setting? Overfitting, of course. We have more unknowns than the number of observations. So it's a simple, our undergraduate linear algebra thing. We have more unknowns and less number of equations. We can't fully solve it. We will have overfitting. So what we need is some sort of mechanism to deal with that. We also can have large computational and memory overhead. Now, this high dimensional problem has existed for decades. There are now books out there. You can read up on these. These are two of the books that I've shown on the picture. And the idea is use intrinsic low dimensional geometry of high dimensional data through the use of an appropriate regularizer. And we have been working with these regularizers for, again, decades. So one of the most popular regularizers that most of you probably are aware of is what's called a sparsity-based regularizer. Let's impose, so this is a picture of basically a union of subspaces which represents sparsity in high dimensional space. And we have used sparsity for sparse regression, sparse approximation. The most well-known example perhaps is compressed sensing, dictionary learning, so forth. We have used sparsity as a regularizer to a very large extent, very successfully. Okay, what is another regularizer? Well, that regularizer is a low rankness based regularizer. So now you can say that, well, the unknown that I have is a matrix, let's call it B, which is P1 by P2. So the number of unknowns here is P1, P2. But let's assume that the matrix is actually low rank. So it can be given as a product of a thin matrix U and another matrix V, so UV transpose. What's the advantage? Well, if the rank is R, then the number of unknowns you have now is P1R plus P2R, okay? Or P1 plus P2R rather than P1 times P2. So P1 times P2 can be large, P1 plus P2 is small, and so that's why low rank regularizers work very well, matrix regression, completion, principal component analysis, all that. So let's talk about what happens when we apply these regularizers. We talk about these regularizers in the context of what's called sample complexity. We say that how many observations do I need to make sure that the solution makes sense? And these are very well, the results for these are very well known. For example, for sparse regression, if you say, I have a sparse vector that I'm trying to estimate, a classical result is, well, you need observations which is on the order of the sparsity times the log factor. You know, the log factor we don't care much about, but it's really, since you say it's a sparse vector, the number of unknowns is more or less S times some locations of where those non-zero entries are. We need to estimate effectively S parameters, N equal to S log P is our sample complexity result. The other result about matrix regression, again, is that you have the number of observations you need is order P1 plus P2 times R, which is, again, the number of fundamental degrees of freedom in your problem. So this looks pretty good, right? We are able to apply regularizers and solve the problem. Except that now we are moving towards problems which are multidimensional. So we use the term multidimensional or multiway or tensor data to think of things that they are not like matrices. They are either 3-dimensional cubes or 4-dimensional or 5-dimensional. The classical example is, of course, a colored image. A colored image is 3-dimensional, right? You have X spatial dimensions and you have 3 color channels. You can have multispectral images. You can have videos which have spatial dimensions and a time dimension. And if you add hyperspectral, you are going to get 4 dimensions on that. So these tensor data, which I'm going to represent by cubes and 3-dimension cubes, because I'm not good at drawing 4-dimensional or higher objects. This is a third-order tensor. We call it a third-order tensor, or you can think of it as if you are doing MATLAB, for example, it's a 3-dimensional array. So the dimensions of this are P1, P2, P3, okay? And the issue is that when we talk about tensor data, even when we are talking about seemingly small problem, actually the data becomes humongous in terms of its dimensions, and our regularizers that we were using, like sparsity, they don't work well because the numbers don't make sense. So let me give you an example. Let's say that I have this tensor, this fMRI image, and this is 256 by 256 by 64. So 256 dimensions this way, and 64 dimensions. Okay, let's say that you want to now estimate this tensor. And you use your classical method, which is that you vectorize this. So you vectorize this into a vector. Well, what's the dimensionality of this vector? The dimensionality of this vector is 4 million. So now go back to the idea of sparsity. Most sparse things, the rule of thumb is like, okay, 5 to 10% sparsity gives you good result. Apply 10% sparsity here. I am looking at least 400,000 observations. So if I was doing a medical study with this, and this is just a toy example, but still to give you an idea, if I was doing a medical study with this problem and I had I'm trying to estimate 4 million parameters, and I'm asking, well, if I apply sparsity-based regularizer, I need 400,000 observations, 400,000 patients in my study. Most medical studies do not have these many patients in them. So that's where you can see that even applying the prior years regularizers, the problems break down. So what do we know? What do we need? We need regularizers that are what we call tensor, not tensor agnostic. They exploit the tensor structure. Okay, so this idea that you need to exploit tensor structure for high dimensional inference, of course, is not new. The goal is that you want to use regularizers that exploit tensor geometry based upon one of the most popular ways is based upon tensor decompositions. I have listed 4 references here because there are way too many works. Here are some references that are broad in their coverage of the topic. They provide summaries, and I recommend that you go and take a look at it. In this talk, I'm going to basically add at some level to these references by talking about 2 particular problems that have not been very well addressed or addressed to the extent that we would have liked. One is the idea of tensor regression, and the other is the idea of tensor dictionary learning. The tensor regression work just appeared in Science Journal of Mathematics of Data Science. The tensor dictionary learning work we have been doing for about 3 years or so. The latest work just appeared. The code has been released on our website, and this is just some of the references. We have more that are available from the website. So hopefully, I have motivated you enough as to when we are dealing with tensor data, why we are in the high dimensional regime, and why do we need new regularizers. If there are any questions at this stage, I'm happy to take them, or I can keep moving. If there anything popped up, the organizers can let me know. Otherwise, I'll keep going. Okay, so let's talk about then high dimensional regression. The problem I'm looking at is the following. We have tensor X, which is what we observe. We call it the tensor of predictors, or tensor. So this is what we observe, and we also observe a corresponding output related to that. So this is a scalar. This is a tensor. So let's set this, the notation and the terminology right. This Y is the response. For example, the response could be that someone measured the fMRI images and declared whether someone has ADHD or not. So the response is yes, ADHD, no ADHD, or some other disease or whatever you are trying to figure out. This X is known to us. This is like, for example, your fMRI brain image. So this is what we call feature tensor. This is observed. So the feature tensor is observed. The response variable is observed. It's classical regression problem with tensors. And then I have regression parameters, which of course, if this is tensor, then my regression parameter is also tensor. I call it regression tensor. And the observations we assume are given by a linear combination of all of my features. So it's a linear regression problem. Plus, I have noise. I've already told you why we can't solve this linear regression problem in the classical setting, because then I would apply something like lasso with sparsity, and I don't have enough observations to actually satisfy that. I'll give you an example later where you will see that how something like lasso doesn't even work for many of these problems. Okay, so the idea is you want to estimate the parameter. So I'm going to shift from, I'm using the notation of more statistics, where B is my unknown rather than X in this problem. So X is actually known, X1. I have one subject, I get its MRI image, fMRI image, I get observation Y1, and there is a tensor parameter that I need to figure out, this B. Of course, I can't estimate this by one observation. So what I would do is I will have N subjects, Each one of them would have different images, different outcomes, but the idea is that all of them, the outcome is a linear combination of your fMRI image in the same way. Now, what is the challenge? The challenge is that the unknowns in this three-dimensional tensor are P1, P2, P3, which I'm going to denote by P. So P is the product of all three. And the number of observations that I have, the number of subjects I have in my study is way smaller than P1, P2, P3. Okay. So let's put it mathematically then. What I have is I have n observations. Each observation is given by an inner product, a linear combination of entries in my features with the unknown regression tensor. The tensor of predictors, now I'm generalizing it. I actually can generalize it to kth order tensor. I don't have to stick to 3. I can go to k. So it's P1 up to Pk. The tensor of regression parameters, which is unknown, is P1 up to Pk also. So how many actual degrees of freedom that I see, extrinsic, that's P product of all the Pks. I have scalar response, I have modeling additive noise, and the goal is to estimate this tensor B using my observations xi, yi. Classical linear regression, except that I am saying B is a tensor. And so the challenge is, this is ill-posed even for small values of P1, Pk, up to Pk. Very small values, n is so small, you can't solve it using classical methods. Even though it looks classical, you can't solve it. So what do? We impose additional structure on the tensor to reduce its intrinsic degrees of freedom. And this is, of course, not a new idea. There are actually, I have listed some references, and there's ... at the end to say that the works continue. Starting from 2011, we're starting work on that. The thing is, in most of these things, the structure that is imposed on your unknown tensor is called low-rank Tucker decompositions. So, so what we have is, let's assume, I'm again jumping to 3 dimensions so that I can show you this pictorially. You have this 3-dimensional tensor P1, P2, P3. And Tucker decomposition basically says that you can effectively write it as another tensor, small tensor, or low-rank Tucker, which has dimensions R1, R2, R3. We call this core tensor. And then you have 3 additional matrices, U1, U2, U3, that actually multiply in each direction of this tensor. For people who are not familiar with tensor literature and maybe having a hard time thinking of that, I'm going to give you an analogy, which is that think of this B as a 3-dimensional, let's say, image, and you this Tucker decomposition, at least in your head, you can imagine this looks very similar to, let's say, a 3-dimensional Fourier transform, right? So the core, the tensor sitting in here is sort of like the Fourier coefficients of your tensor. And the U1, U2, and U3 are your Fourier bases that go hit your columns and your rows and your depth, okay? Except that in this setup, I'm not going to assume that my core, I'm not going to assume the dimensions are not going to be the same. In fact, the idea is that the core tensor has dimensions R1, R2, R3, and it is low rank because R1 is much smaller than P1, R2 is much smaller than P2, and R3 is much smaller than P3. And these matrices U1, U2, U3, which hit the different modes of your tensor, the core tensor, they have dimensions than P1 by R1, P2 by R2, and P3 by R3. So, and they are not orthogonal, right? So they are not orthogonal or unitary matrices. So that's sort of the difference. Mathematically, what we can write is that this B is given by a linear combination of outer product of 3 vectors. And this is basically a vector. This is a rank 1. What we say is that it's a linear combination of rank 1 tensors. For people who are familiar with CP decomposition, which is another form of tensor decomposition, the difference between CP decomposition and Tucker decomposition is that in Tucker decomposition, actually these rank 1 tensors share some of the columns with each other. So another way of writing this is that you have this core tensor G, and then in mode 1, you hit it with the matrix U1. In mode 2, you hit it with matrix U2, and in mode 3, you hit it with matrix U3. Okay, so if you were writing a 3-dimensional Fourier transform, you could effectively just write it like this if you were being taught 3-dimensional Fourier transform. Except that, as I said, the dimensions will be different. Okay, so this actually existed, and what it turns out is that in one of the latest works in low-rank Tucker model, Rahut et al. Actually figured out what the sample complexity of this problem can be, and they showed that the sample complexity is P times R times K, where K is the order, plus R raised to the power K. So R raised to the power K is the number of parameters in your core tensor, and PR is the parameters in each of your matrix, and K is the total number of matrices that you have. So this is effectively the total number of degrees of freedom you have, the intrinsic degrees of freedom. Except that the sample complexity of this problem can still be infeasible for large values of Pmax. So if Pmax is pretty large, you can imagine if any one of the dimensions were large, this product P times R could be pretty large. That's one of the issues with this. The other is that this model doesn't give rise to parsimonious regression parameters. So one of the things we are interested in regression is that can we identify, for example, some of the things that influence our outcome the most, like perhaps certain parts of the brain are affecting whatever we are observing the most. This model doesn't impose that. So what do? Well, we pose a different model. We pose a model we call low-rank and sparse Tucker decomposition. And the idea is that now, instead of saying that you have these factor matrices, U1, U2, U3, we also say that the factor matrices columns are sparse. So we have a Tucker decomposition, except the core tensor stays the same, but the factor matrices have sparse columns. And if you actually break it down to 2 dimensions, you can relate it to the concept of, for example, sparse principal component analysis. So now we have 2 parameters, 2 degrees of freedom to play with. One is low rankness, but we also have sparsity. And so the definition of low rank and sparse Tucker decomposition is that a tensor admits a low rank and sparse Tucker decomposition if it can be written in the form of a Tucker decomposition. And then the core tensor, the dimension of that, this is element-wise inequality, is much smaller than the individual dimensions of the original parameter tensor that you are trying to estimate. And also, the columns of each of your matrices has dimension S, has at most S non-zero entries. And each one of those is much smaller than P1 also. So why do that? Well, because it has done 2 things. One is you can imagine, you can see, in fact, that now it has reduced the number of degrees of freedom we have to estimate in each matrix U. From PR, degrees of freedom in each matrix, we went to SR. The second is that if the sparsity is very high, then in fact, that's not always going to happen. But if the sparsity is very high, it's going to start imparting sparsity to my parameter tensor. Okay, so that's the added benefit. Okay, so then the notation is what we have is a model for low rank and sparse Tucker regression. We say the same model, we have observations which are linear combination of my features. The predictors are P1 to Pk dimensions of tensor. I have parameter tensor B, which I need to estimate, but the parameter tensor B is RS Tucker decomposable. R is an ordered pair of R1, R2, R3. S is an ordered pair of S1, S2, S3. And what it means is that the core tensor is R1, R2, R3, and the factor matrices have no more than S non-zero entries per column. And we have scalar observations. All of this, we write it in a compact form. If I get all of my observations, put them in a column, I get a column vector Y, which is n-dimensional, and I write it as this operator X operating on the parameter tensor B, where this operator X is now just a linear operator that acts on the space of tensors. And the ith entry of this operator is simply inner product between my observations and the unknown parameter tensor. So this is just a compact form. And what we want to do is two things. One is we want to come up with an algorithm that is provably convergent in estimating B. And the second is we want to characterize the sample complexity of the developed algorithm. Okay, so so this is where we have set the stage. We are interested in doing low rank and sparse tensor regression. I presume there are no questions. Otherwise, the organizers would have let me know. So I'm going to keep moving. So here is the algorithm. The algorithm that we have is a simple goodness of fit kind of criterion, except that, so what we do is we take our observations, Y, and we try to fit a tensor that fits our observation. So we are trying to minimize the means, the L2 error, except that the tensor that we are fitting must belong to the space of R as Tucker decomposable things. So it must be low rank and sparse. Okay. So what is the algorithm we propose? The algorithm we propose is a simple, we call it tensor projected gradient descent. It's a simple gradient descent algorithm, which is projected gradient descent, which is we basically, in each step, we carry out a gradient step, which is just take the previous iterate, have a step size mu, and then this is your gradient for the multilinear problem. This is the adjoint of your operator. And then once you do that, then you do a projection step, which is you take whatever you obtained and you project it onto the space of low rank and sparse Tucker tensors. Except that computing this low rank and sparse Tucker decomposition is not very easy. So what we do is we have a side algorithm for that. So the projection step, so what we are interested in is how do you actually take a tensor and project it onto the space of, you have W and you say, I want to find the best approximation of that in the space of low rank and sparse. Well, luckily, we can use something like sparse higher order SVD, which is an algorithm proposed by Genovese Allen in 2012, which is the idea is very simple. It uses sparse principal component analysis, which I already told you is the connection between the two things, which is you are given a tensor W. What you do is you first take your tensor W and you matricize it in mode K. What is mode K matricization? That you stack mode K fibers into columns to make a matrix out of it. So for example, mode 1 matricization is just taking all the columns of your tensor and putting them into a big long, unfolding it into a big long matrix, right? And similarly, mode 2 is taking the rows and so forth. So what this algorithm does is it basically goes through, it takes the mode K factor matricization, and then it computes a sparse principal component analysis and declares that to be your mode K matrix that you are after. And then it finds your core tensor as simply taking your original tensor and projecting it onto this sparse PCA basis. Okay, so that's sparse higher order SVD that we use. And based upon that, we can actually give an algorithm for the convergence of TPGD. The algorithm relies on a similar concept that exists in many other of these regularized problems, which is that the operator acting on a restricted space preserves energy. So within the restricted space, there is no null space effectively for the operator. So here the idea is my operator is X that is acting on sparse low rank tensors. For all low rank and sparse tensors, the operator must preserve energy of that tensor. Okay. And if you look at that, then we can provide a convergence analysis. Let's dig into this a little bit. I see there are a couple of chat messages popping up. If I should take them, then the organizers can tell me.
So Waheed, that was a question about I think it's about the previous part of the talk, where so an audience asked whether we can extend Y to have multiple dimension.
Extend which one to have multiple dimensions?
I think the Y, the observe or the response from the subject.
Oh, yeah, yes. There are extensions of that. You can basically have Y to have so just like in linear regression generally, you can have scalar response, you can have vector response, you can have tensor response. So exactly here you can go from the problem we were interested in was ADHD, where the response was scalar, which I'll show later. But absolutely, if you have a problem that is extendable, would the results extend? That I don't know. But the problem setting is extendable, and there have been some works on at least vector valued ones. Thank you for the question. Okay, so let's dig into the result. What is the result saying? The result is saying that, so the assumption is, of course, that you have the tensor belongs to the space of low rank and sparse tensors, and your map X, which is the map of your features, satisfies the RIP, which is not too small. Then using a fixed step size, so we are allowing the step size to be fixed, we have, what we get is a geometric linear or linear rate of convergence, whichever community you come from, you call it geometric, you can call it geometric or linear rate. So this gamma to the t, so this is geometrically decaying, this error is geometrically decaying, plus a term due to, so this error depends upon where you initialized, plus an error term due to noise. And of course, the noise term scales linearly with deterministic noise power. Okay, you can make it for the case where the noise power shouldn't scale within the worst case or deterministic sense. We haven't extended that, but that's also doable. Okay, so basically what it says is, well, if you didn't have noise, first of all, you will recover your parameter tensor exactly. And if you did have noise, then you can run enough iterations and you will get to the right solution. Of course, there is a big catch, which is that, are there really linear maps that operate on tensors that satisfy the RIP? So the answer is yes, and we again do the same thing that many people do to show existence of these linear maps. We study them for sub-Gaussian linear maps on tensor spaces. So assume that each of those xi tensors that I showed you, assume that they come from sub-Gaussian random variables with parameter alpha. What's sub-Gaussian random variable, for people don't know? It's the one whose moment generating function is dominated by that of a Gaussian variable, or effectively its tail is dominated by that of a Gaussian. So its tail is no fatter than the Gaussian tail, effectively. Okay, if you want to think of it. And examples, of course, are Gaussian, bounded, uniform, binary, all of these things. And the result is that indeed, if I took my linear map that acts on the space of my parameter tensor to be from this sub-Gaussian distribution, then it satisfies the RIP. And the number of samples you need to satisfy the RIP is given by Sk times Rk. Remember, Sk Rk is the number of parameters per matrix Ui. So you have k of them, so Sk Rk summation, and product of Rk, which is the number of parameters that your core tensor has. So no surprise there, we are able to get to a result which actually is proportional to how many degrees of freedom you have, plus a log factor. So if I compare this to the results, here are some of the results. For simplicity, let's assume that everything is equal dimension. P1 equal to P1, 2 equal to Pk equal to P bar, R1s are R bar, and S1s are S bar. If you compare the results, some of the first results that came up for regression tensor, its complexity scaled exponentially with P to the K minus 1. Then we had another result that actually decreased the complexity. Then Rahut's result decreased it considerably, but it is still a function of P. So R times P times K. And we are saying, well, you can actually you can replace P with S. So what do these numbers look like? So we played around with some neuroimaging data set, and we saw that K equal to 3, P bar equal to 128, R bar equal to 3, and S bar equal to 10. So effectively the same principle that we said, right? So in most cases, the relationship between the exterior or extrinsic dimension and the sparsity is about, 10% is a good rule of thumb, right? So what happens is that we are able to reduce the number of the sample complexity requirement by a factor of 10, effectively, by imposing this sparse and low rank rather than just low rank Tucker. Okay, but the idea is like, does it work? Yes, I can prove theory for many things, but does it really work? And if I do that, so let's take a look at some synthetic experiments first. So let's take the example of a regression tensor 50 by 50 by 30. That's 75,000. And R1, R2, R3 is 3, S1, S2, S3 is like really small dimensions, right? About, you can say 10%, roughly 10%, 56, 56, and 34. So roughly 10% sparsity. And then we have randomly generated coarse tensor, and the Gaussian regression map is this, and we add noise, we get the observation, and then we compare to the sparse regression, low rank CP regression, low rank Tucker regression. And then I go to the results and I don't show you lasso at all. And the reason is that if I think of it as just linear regression problem, my degrees of freedom, my external dimensions, P is 75,000. And you see that on x-axis, I'm going up to about like 1,400. This is just such a high dimensional problem. The number of observations is just such a small number that something like lasso doesn't even work. So I could plot it, but it just doesn't work at all. And here are the results which show that all the methods, of course, work, but effectively it's where their needs are, right? The TPGD starts working better. Of course, we are a little bit cheating, which is that we are using the model that TPGD uses. So we'll go to the real data, but let me just show you another thing, which is that so our results are high probability results. So we are providing histograms of your normalization error. And you can see that TPGD, our method, and Rahut's method, PGD Tucker, they are mostly performing well, whereas PGD CP doesn't perform well. It's a scatter shot. And then here is a what's called a violin plot, which shows that how well the things are concentrating with increasing number of observations. And you can see that for n equal to 900, our method has really concentrated around this. PGD Tucker is still kind of going a little bit off, and PGD CP, the CP rank based one, is all over the place. Okay, so this is synthetic data. Let me let me now give you a quick real world example, which is that of this ADHD study, ADHD 200. It's a collaboration of imaging sites that have subjects, and they are trying to understand what are the aspects of your brain that can cause ADHD, which is attention deficit hyperactivity disorder. We use the data from 3 sites, NYU, NeuroImage, and KKI. The raw data for this was 3-dimensional fMRI. But for this ADHD 200, actually, we have pre-processed data available in terms of what is called fractional amplitude or low frequency fluctuations. And when you do that, this is what it comes out to be. Your P1 is 49, P2 is 58, P3 is 47. So if you do the product, that's 133,000. You say that's not very high dimensional. But remember, high dimensional is relative to the number of samples you have. So look at this. Even if I did a study with all the 3 sites, I have only 305 subjects. I have 305 observations to estimate this big tensor. And in fact, if you divide it further, for neuroimage dataset, I have only 39 samples, out of which 17 are ADHD. And if I did that, this is the TPGD result. true negativity rate, which is like someone didn't have ADHD and how much did you predict that, that's 68%, true positive rate is 73%, and the harmonic mean is 70%. So for both neuroimage and KKI, harmonic mean does very well. Here are lasso results, by the way. Look at this result, right? This is support vector regression. Look at lasso. For this small data set, or even this data set, lasso is just baffled. It's declaring everything to be basically that it's negative. It can't do anything, okay? Here is an NYU data set where the two methods perform very similarly, and one of the reasons that the gap exists is, well, first of all, the number of samples are more, so their performance approaches to each other. And the PGD Tucker and TPGD, our proposed method, you can see that even lasso has started to perform better because the number of samples is pretty high. But one of the distinctions between the two is how we are doing the projection. So this is where I have finished regression, and I'm going to move to dictionary learning unless there are any questions, because I want to give a different flavor where we are now talking about how do we do feature learning for tensor data when we have the similar challenge that we don't have enough samples. I'm going to go a little bit faster in that direction because I think I will soon be done with the time. Are there any questions at this stage?
No, so there's no question at this. Oh, actually, there's one. So one question is about how do we interpret the sparsity in the factor matrix?
So the sparsity in a factor matrix is, at least we haven't been able to interpret explicitly. It is more very similar to the idea of like sparse principal component analysis, which is that you are trying to learn basis where each of the bases is itself sparse because you're trying to reduce the number of parameters. If there is enough sparsity, then their sparsity starts to show up in the B tensor, and there it is interpretable. There, any tensor which is any entry which is sparse, you say that, well, that particular aspect didn't play a role in the decision making. So hopefully that's somewhat makes sense.
I think it's also nice to speed up a little bit because we are now 6:50 already.
Okay, I'm going to quickly cover some of the things, and then if we don't, we'll just wrap that up. So the other idea is what I want to talk about is feature learning. So feature learning, I want to use the example of dictionary learning, which is that now I have data which is m-dimensional, and dictionary learning basically projects your data onto a p-dimensional space, which is the projection is parameterized by a matrix D. So you solve this problem, this restricted problem, effectively sparse coding problem, to go to the space. And the inverse map is simply multiplication of that matrix with X. So if you look at it, you have a observation Y, and dictionary learning is learning a matrix D, which is M by P, so that when you do this mapping from original space to a higher dimensional space, your features are sparse. So now you're learning features which are p-dimensional, and the features are themselves sparse. How do you learn the dictionary? Well, you actually collect n samples. So n is still the number of samples. You put them in columns, and then you get a big matrix Y. You try to approximate it with Y approximately equal to D dictionary times X, where X is the sparse coefficients of each of your samples. And the way you solve that is you formulate this empirical risk minimization problem where you say, well, I have my data, I'm going to do a goodness of fit of that, and also require that the data is sparse, probably add some regularizer to enforce the sparsity, add them up, minimize that. And dictionary learning has been going on for actually 2 decades, but the sample complexity results for dictionary learning only started showing up about 6 or 7 years ago. In particular, one of the earliest works was by Karen Shanas. Beautiful work if you want to look at it. But here is the upshot of these works, which is that the complexity, the number of samples you need, we have actually both upper bound and lower bound. It says that the number of samples you need is it probably doesn't get to be more than MP cubed, but it cannot be smaller than MP squared. And this is impractical for most tensor data because P can be large because M is large, you are tensor data, M is large, so P is going to be even larger, and MP squared and MP cubed are going to be humongous. So how do you do dictionary learning for tensor data then? Well, the way you deal with that is we again bring in Tucker decomposition. We say, rather than actually taking your data and vectorizing it, you have a tensor data sample. So a sparse representation in a dictionary is equivalent to actually having an over-complete sparse Tucker decomposition. Now, it's Tucker decomposition, but look at the relationship is that my original tensor is M1, M2, M3. I now have a Tucker decomposition, but now my core tensor is bigger than my original tensor, and it is sparse. And these matrices, I call them factor dictionaries. They are sub-dictionaries in each mode. So the same idea, except that compared to the previous example, now actually I have expanded my space because I'm mapping my data from lower dimensions to higher dimensions. So I have sparse core tensor P1, P2, P3. I have dictionaries M1 by P1, M2 by P2, M3 by P3. And I can actually now take my sparse, my tensor yj, and I can vectorize it. In that case, its length will be product of m's, and the length of my sparse vector will be product of pk's, which is this sparse core tensor. So if I do that, I get a similar representation as earlier, except that the dimensions are different. And if I vectorize it using a simple linear algebra or tensor algebra fact, what I realize is that a vectorized tensor under the over-complete sparse Tucker decomposition looks like very much a dictionary learning problem, except that my dictionary now has this Kronecker product. This is a Kronecker product notation. So you may ask, like, what did we do? Why did we, if we are back to vectorization, why did we talk about all this? Well, the reason is because now effectively, I have reduced the space of my dictionary. So look at this example where I have 512 by 512 image. If I did an unstructured dictionary and just take the dictionary to not be over complete, take P to be equal to M, I need to estimate 6,871 billion parameters, or 6.871. I might have a period missing. But if I did a Kronecker structured dictionary where each M1 was equal to P1 and P1, P2 was 2 to the 9, then I only have 520,000 parameters to estimate. And so there is a lot of related work that has done this, actually, that has realized this, that by imposing this Kronecker structure, you can get away with the number of samples you need for your feature learning, except that those works don't provide you any understanding of the sample complexity bound. So the way you want to solve this problem is, of course, again, that empirical risk minimization formulation, except that now your dictionary is forced to be this Kronecker product form. And what we have is these informal bounds, which show that, so there is a lower bound, which you compare to the vectorization bound. So vectorization bound says that you need M times P. So P times MP. Whereas our lower bound says you need P times summation of M1 P1 plus M2 P2 plus M3 P3. So a significant reduction of the same way that we thought about in earlier. Then there is an upper bound, which was MP cubed, and we have reduced that to maximum of MK PK cubed. So again, per dimension rather than the entire dimension. And since I'm kind of out of time, I'm going to just quickly go over the fact that all of these results are, of course, assuming that you can solve this problem. How do you solve this problem in a practical manner? There have been some algorithms, but what we did was we actually came up with an algorithm that extends this Kronecker dictionary learning model to what we call a low separation rank dictionary learning model. So we extended the model to saying that actually what you have is Yj is a Tucker decomposition plus another Tucker decomposition plus R of them, but each one of the core tensors stays the same. What is the advantage of that? The advantage of that is that actually you get a little bit more. So if you vectorize everything, what you get is that your dictionary now looks like a summation of chronicle structured dictionaries. So this is called rank R chronicle structured dictionary, low separation rank R. And the advantage is it allows you to basically balance between representation power and sample complexity. And so based upon that, an important lemma that comes up is called the rearrangement lemma, but which actually there is this beautiful result, which is in this our recent paper, which shows that every matrix of this form, low separation rank matrix of this form, can be rearranged into a tensor of CP rank R, and the rearrangement is known. So using this idea, we actually developed two algorithms. The code is on our website. I don't have time to go into the details of these algorithms. One is based upon regularization, which uses ADMM. The other is based upon factorization and uses CP decomposition. And we ran experiments which we compared the denoising performance of our method called Stark and Tefdil with a plain, for example, block coordinate descent or existing methods or K-SVD. And the upshot I will tell you is this. First of all, our method beats everyone else, all the other dictionary learning methods. But here is the biggest upshot, which is that when in the high noise scenario where the variance is very high, so you're not worried about bias, you can actually, with R equal to 1, you have enough expressive power to get a good result, as good as K-SVD, but look at the number of parameters that our model uses versus the number of parameters that K-SVD is using. 147,000 versus 265 parameters. So with this, I will conclude by saying that even though many of the tensor problems can be vectorized, but if you want to deal with the issue of high dimensionality, we have to actually pay attention to the tensor structure. If we didn't have the issue of number of samples, then we don't have to worry about it. I gave you two examples. One was tensor regression. The other was tensor dictionary learning. Full list of papers and code is on our website. With this, I'll conclude, and I'll be happy to take any questions.
Okay, I think there are several questions from the audience. Anyone wants to ask?
Let me first forward several questions that I have been monitoring.
Please.
Thank you, Waheed. So Liao Liang asked that. Liao Liang, do you wanna rephrase your question and ask it by yourself? Because the question here in the chat box is a little bit terse. Okay, so let me forward the comment. So the comment is, I think I probably can generalize these algorithms over a commutative algebraic ring. They have a theory of a new algebra which generalizes the field of the complex numbers and generalize these algorithms in a back-forward compatible manner. So that's the comment. There's no specific question. So Waheed, do you hope to respond to this?
Well, as you said, it's a comment. I appreciate the feedback. I guess I didn't, when it was said that these algorithms, there are different algorithms that I actually discussed. Were they for dictionary learning or were they for the tensor regression one? In either case, I would be very happy to see the works that he's referring to. So please we can either stay back after this talk and chat, or you can forward them to me, send me an email. I would love to talk more about it.
Yeah, I prefer to send an email because that's a long story to discuss here, because our research is mainly about a very fundamental mathematical framework. In summary, we have developed a new algebra which generalized the field of complex number. That means if we can generalize complex number, in other words, we have a model generating scalar. We have a generalized scalar. If you put generalized scalar as entry of matrix or as vector or even as the entry of your tensor. So everything, I think many things, if not all, can be generalized over the new algebra. We have already published 2 papers. The first one is already published by Spring. Another one has recently completed, and we have already put it open access online, but still need 2 days to be announced by archive. In summary, it's a long story, I think, to give more detail in this seminar. But I can, if you're interested, send an email, contain the link of the 2 papers to your email. I think not only your algorithm, probably many more algorithms using vector or matrix or even tensor can be generalized in this straightforward, backward compatible manner. If you're interested, I would like to share my information.
Sure, we can follow it up over email. Thank you so much for
Thank you very much for your comment. Thanks. Another question is also something I would like to ask. That's from my PhD advisor. Professor Wen-Kim Ma asked that, so the projection step in the first algorithm that you used, the regression method, is basically you used this sparse high order SVD to implement the projection, right? My understanding is that if the projection part is solved to optimality, then the linear convergence rate holds, right?
Yes.
So Professor Ma's question is that, is there any guarantee for this projection step?
Right, so the short answer is no. The long answer is that we have 2 pieces in our treatment of this topic. So sparse PCA, even which was tried for a long time, actually the results on sparse PCA came out only in the last 2 or 3 years in terms of how well can you do sparse PCA, especially in the low dimensional setting, or sorry, in the high dimensional setting. So this sparse higher order SVD, or this projection step, it's completely, the one we used in algorithm is completely arbitrary. It's just that, it was there, it was based upon sparse PCA, which was very simple. So we used it. But our analysis is just based upon if you can do this projection. And that result actually exists in pretty much all of the Tucker-based regression models. Like if you look at Rahut's work also, it's like, if you can do this projection, then this would happen. So unfortunately, there is that piece missing. But also you can say, fortunately, there is that piece missing because there is more to do then. Yeah, so that's the long answer. And the short answer is absolutely right there. And that's where I actually pointed out that why we can't really conclusively say when the algorithm doesn't perform as well as the PGD Tucker, why we can't conclusively say much, because we believe that's due to the projection step. And I can talk more about why we believe that.
So may I better understand a little bit more then? Now, since you provided certain theoretical result on the sample complexity. Now, what does that referring to? Is it when you optimally solve the problem?
Yes, exactly. Assuming that you have a projection algorithm that actually solves that problem exactly, then you have the sample complexity result. There is also
or even more, you exactly solve the original problem.
Exactly.
Now, because you're going to use projected gradient, right? But the projected gradient could still get stuck at local minimum.
No, as long as the projection step keeps on working fine, then the local minima part is okay. So let's put it this way, right? Under the RIP assumption, those local minima would not arise in that setting, right? So under the space, because we have now made it's the same reason that, like, for example, FISTA or something like that in compressed sensing works under the assumption of RIP. So the issue that you are mentioning is taken care of through RIP.
I see. Thank you.
So I have a follow-up question. Perhaps we have time for one question. So I'll take that chance because I'm super interested in this direction. So so I'm curious, Waheed. So you are using this. What is the tool you are using to derive the RIP for your case, right? Because I remember in Rahout 2017, that paper. So they basically they used the tensor covering number, if I remember correctly, right? And to derive that covering number, they need to assume that U1, U2, U3 are orthogonal, right?
Right.
So that they would have something similar to the Edgar-Young property in the matrix case. So I'm wondering if you have assumed that U1, U2, U3 to be orthogonal.
Actually, that is one of the major differences with Rahout's work, that we don't require orthogonality. We, of course, at the end of the day, there are only so many tricks in the bag, right? So we are also using the covering number, but we have to build an epsilon net over both the space of the sparse vectors, or these sparse vectors within your bases and your cotensor. But we don't require that orthogonality. And the reason we don't require the orthogonality is because we are imposing sparsity.
I see.
So by imposing the sparsity, we actually also lower one of the requirements that was needed. We are able to prove even without that.
That sounds interesting because so later I'll send you one of my papers that we derived covering number for CP tensors under the regression model. So I'll have more discussion with you. So let me forward one more question from the audience to you. Howard Young asked, is the high dimensional tensor regression method robust against, for example, outliers? Have you considered this?
So again, the short answer would be, I haven't tested, but I would be surprised if it is. Just like any other algorithm in statistics, robustification, very infrequently robustification happens by itself. You have to add robustification and, to in some way. And so I would be actually very surprised if it is robust. We haven't tried it, but I would be pretty surprised if somehow magically it is robust. That's the whole reason the field of robust statistics exists, which is that you often have to robustify these methods. I presume it wasn't a very informative answer, but that's the most honest answer I can give.
Okay. All right. So I think we should wrap up the seminar. So let's thank the speaker again. And so our next talk is in 2 weeks. So we will be sending you reminders, and please check your emails for the information of a Zoom link and YouTube link. So let's thank the speaker again.
Thank you, everyone.